Picture the most harmless object you can imagine. A sewing needle, 3 centimeters of steel, so light you'd barely notice it resting in your palm, so thin you could lose it in the folds of a blanket and never find it again. Now imagine that same needle, unchanged in every way except one, streaking toward Earth at the speed of light. Not close to it, not almost there. Exactly at 792,458 meters per second, the ultimate speed limit of the universe. What happens in the instant it touches the atmosphere is not a story about a needle at all. It's a story about the strange, almost cruel arithmetic hidden inside Albert Einstein's most famous equation, and about why the universe seems to have built a wall around the one thing that would make the answer to this question truly unbearable. Here's the twist right away, before we go any further. This can never actually happen. Not with better rockets, not with future technology, not even in principle. According to special relativity, any object that has mass, no matter how small, would require an infinite amount of energy to reach the speed of light. Not a lot of energy, not more energy than exists in the universe. Infinite. That's not a technological hurdle we might one day clear with clever engineering. It's a hard boundary built into the geometry of space and time itself. So strictly speaking, a needle can never hit the Earth at the speed of light. Full stop. But physicists love this kind of question precisely because it's impossible, because pushing a thought experiment to its breaking point is often the best way to understand the rules that make it break. So let's do what curious minds have done for over a century. Sneak right up to that wall, get as close to light speed as the mathematics will honestly let us, and see what waits on the other side. To understand why a needle could ever be dangerous in the first place, we have to go back to a piece of physics so famous it's practically a cultural icon, yet so often reduced to a slogan that its real meaning gets lost. Einstein's equation, E equals mc squared, says that energy and mass are not separate things. They're the same thing, expressed in different currencies, and the exchange rate between them is the speed of light multiplied by itself. Because the speed of light is such an enormous number, that exchange rate is staggering. A tiny amount of mass converts into a tremendous amount of energy. This isn't just theoretical bookkeeping. It's the same principle that powers the sun, the same principle behind nuclear weapons, the same principle that lets a reactor generate electricity for a city from a fuel rod you could hold in 2 hands. So let's apply that idea to our needle. Say it weighs about a gram, roughly the mass of a paperclip or a small steel sewing needle, just sitting there, doing nothing, not moving an inch. That single gram of mass is equivalent to something like 21,000 tons of TNT if you could somehow convert all of it directly into energy. That's already in the same neighborhood as the atomic bomb dropped on Hiroshima, and that's before the needle moves at all. That's simply the energy locked inside its mass, according to the deepest bookkeeping rule of the universe. Most of the time, we never see this energy, because converting mass into pure energy is extraordinarily difficult. It's the domain of nuclear fission, fusion, and matter-antimatter annihilation, not everyday collisions. But when an object starts moving at extreme speed, a different piece of the same equation kicks in, and this is where our thought experiment really takes off. When something moves, it carries kinetic energy, the energy of motion. In the everyday world, kinetic energy behaves in a very tame, well-behaved way. Double an object's speed, and you quadruple its kinetic energy. And that's the physics you learn in a high school classroom, and it works perfectly well for cars, baseballs, and falling apples. But that simple rule is actually just an approximation, one that only holds true when speeds are small compared to the speed of light. As an object's velocity climbs higher and higher, approaching that ultimate cosmic limit, the old formula breaks down, and a new, far stranger relationship takes over, relativistic kinetic energy. This is governed by something physicists call the Lorentz factor, a number that starts at 1 for anything sitting still or moving slowly, and then begins to climb, gently at first, then explosively, as speed approaches the speed of light. Here's the part that should genuinely unsettle you. At 10% of light speed, the Lorentz factor is barely different from 1. Classical physics still works just fine. At 50% of light speed, you start to see real deviation. At 90%, the correction becomes significant. But push further to 99%, then 99.9%, then 99.99%, and the Lorentz factor doesn't just keep climbing steadily, it runs away. Each additional 9 you tack onto the decimal makes the number surge upward by leaps that dwarf everything before it. This is the real reason particle accelerators need to be so enormous and consume so much power just to nudge subatomic particles a fraction closer to light speed. You're not fighting friction or air resistance up there. You're fighting the geometry of space-time itself, which seems to defend the speed of light like a fortress wall that gets thicker the closer you approach it. Let's put actual numbers to our needle and watch this play out. If that 1 gram needle were moving at 99.9% of light speed, its kinetic energy alone, above and beyond the energy locked in its rest mass, would already be in the range of hundreds of kilotons, tens of times more powerful than the bomb that devastated Hiroshima. Push it further to 99.99% of light speed, and the number leaps again. The kinetic energy climbs into the range of roughly 1.5 megatons, comparable to some of the larger thermonuclear weapons ever built by human hands, an amount of destructive power that could level a city and scar the landscape for miles in every direction. And we haven't even reached the truly absurd digits yet. Nudge the needle to 6 nines after the decimal point, 99% of light speed, and its kinetic energy balloons past 15 megatons, roughly a third of the yield of the Tsar Bomba, the most powerful nuclear device humanity has ever detonated. A weapon so enormous its test in 1961 shattered windows hundreds of kilometers. Away and sent a mushroom cloud higher than 7 times the cruising altitude of a passenger jet. Add 1 more 9, and our single gram of steel, an object smaller than a grain of rice in terms of mass, carries kinetic energy rivaling that 50 megaton monster outright. Sit with that for a second, because it's genuinely one of the strangest ideas in all of physics. We are not talking about a boulder. We are not talking about an asteroid, or a meteor, or anything with real heft behind it. We are talking about a needle thin enough to thread through a shirt button, and yet, by the time it's traveling close enough to the speed of light, it carries an amount of destructive energy that belongs in the same conversation as the most powerful weapons ever built. Mass, it turns out, is almost beside the point at these speeds. Velocity becomes the dominant variable, the great multiplier, capable of transforming even the most insignificant object into something civilization threatening purely by how fast it's moving. This is precisely why physicists sometimes say that at relativistic speeds, everything is a bullet. Size and mass stop mattering nearly as much as speed does, because speed is squared, then run through a runaway relativistic correction that has no upper limit except the one nature refuses to let you cross, which brings us back to why nature refuses to let you cross it. That barrier isn't arbitrary. As an object's speed climbs toward light speed, its relativistic mass, in a loose but useful way of thinking about it, keeps increasing. That means it takes more and more energy to add each additional increment of speed. Near light speed, you could pour in energy indefinitely and still only close the gap by a smaller and smaller fraction, forever approaching but never touching that final limit. It's a bit like trying to walk halfway to a wall, and then halfway again, and then halfway again. Mathematically, you get closer and closer, but you never technically arrive. Except in this case, the halfway steps require exponentially more energy each time, until reaching the wall itself would demand an infinite reservoir of energy that simply does not exist anywhere in the universe. This is why physicists consider the speed of light not just a practical limit, but an absolute one, baked into the structure of space-time the way the number 3 is baked into a triangle. Now, here's a wonderful and slightly humbling twist. Nature has already run something very close to this exact experiment for us, without any help from human engineers. Cosmic rays, streams of subatomic particles racing through the universe, occasionally strike Earth's atmosphere carrying jaw-dropping amounts of energy. In October of 1991, a detector in the Utah desert called Fly's Eye recorded a single particle, likely a proton, arriving from deep space carrying roughly 320 exa-electron volts of energy. To grasp how absurd that number is, consider this. Physicists nicknamed it the "oh my god" particle, and for good reason. That single, unimaginably tiny particle, thought to be moving at something like 99.99119. 9% of the speed of light, carried the kinetic energy of a baseball thrown at highway speed, all bottled up inside a subatomic fragment of an atom you couldn't see even with the world's most powerful microscope. Scientists are still not entirely certain what could have flung a single proton to such an extreme velocity, whether it originated from some violent event billions of light years away, perhaps near a supermassive black hole or the aftermath of an exploding star, or from some cosmic accelerator process we don't yet fully understand. What we do know is that such particles strike our planet's upper atmosphere regularly, and that every single time, our thick blanket of air absorbs the impact long before it can reach the ground, scattering that violence into a harmless shower of secondary particles high above our heads. That detail matters enormously for our needle thought experiment, because it tells us something crucial. Even if we could somehow accelerate a needle to relativistic speed and aim it at Earth, it likely wouldn't survive its final few hundred kilometers of travel intact. The atmosphere isn't just empty space. It's a dense, invisible ocean of nitrogen and oxygen molecules, and slamming into it at even a modest fraction of light speed would be like driving into a wall made of concrete. Except in this case, the concrete is invisible and the needle is moving so fast that the interaction would strip away and ionize its atoms almost instantly. The kinetic energy wouldn't wait patiently for a clean impact on the ground. It would begin dumping itself into the surrounding air the very moment the needle crossed into the upper atmosphere, triggering a cascade of interactions, not unlike the extensive particle showers cosmic rays produce, just concentrated into a violent flash instead of spread out gently over dozens of kilometers of altitude. In other words, the impact wouldn't happen at the ground at all. It would happen kilometers above our heads, releasing its devastating energy as an airburst, a blinding flash and shockwave, not unlike a small nuclear detonation triggered high in the sky, similar in character if wildly different in cause to the way a large meteor might detonate in the atmosphere before ever reaching the surface. It's worth pausing here to appreciate the almost poetic irony buried in this thought experiment. We started with an object we associate with delicacy and precision, a tool for the smallest, most careful human tasks, sewing a hem, popping a splinter, threading a bead. And through the lens of relativity, we've turned it into something that could rival, or even exceed, the most destructive weapons ever built by our species, simply by asking what happens if you push its speed high enough. That's the peculiar genius and the peculiar horror of Einstein's equation. It doesn't care what the object is. It doesn't care whether it's a needle, a grain of sand, a pebble, or a spaceship. All that matters is mass and velocity plugged into an unforgiving formula that treats every kilogram and every fraction of light speed with the same cold mathematical indifference. The universe doesn't distinguish between harmless and harmful the way we do. It only understands energy, and energy, once concentrated enough, is always dangerous, regardless of what container it happens to be wrapped in. To really appreciate the scale we're discussing, it helps to zoom out and compare our hypothetical needle strike to real catastrophes written into Earth's own geological memory. The asteroid impact, widely believed to have ended the reign of the dinosaurs some 66 million years ago, the one that carved out the Chicxulub crater off the coast of what is now Mexico, is estimated to have released energy on the order of tens of thousands of megatons, roughly equivalent to detonating 1 billion Hiroshima-sized bombs at once. That impact came from an object roughly 10 kilometers across, a genuine mountain of rock and ice slamming into our planet at cosmic speed. Our relativistic needle, even pushed to its most extreme, most physically implausible velocity, still falls short of that kind of civilization-ending, extinction-level devastation. It would be a regional catastrophe, not a planetary one. A horrifying, city-erasing event, not something that would end life on Earth. And that, too, is a strangely important lesson tucked inside this thought experiment. Even relativistic speed, the fastest anything can theoretically move, cannot fully substitute for genuine planetary scale mass. There's a reason astronomers who study planetary defense worry about kilometer-sized asteroids and not about high-speed dust grains, even though, gram for gram, a fast enough dust grain could theoretically outshine a nuclear weapon. Scale still matters. It's just that our intuitions about which kind of scale matters, mass or speed, turn out to be badly miscalibrated once relativity enters the picture. There's another layer of wonder hiding inside all of this, one that connects the needle sitting in your sewing kit to some of the grandest structures in the cosmos. The same equation that tells us a relativistic needle could flatten a city also tells us how stars generate the light that has warmed planets for billions of years, how the sun converts a tiny fraction of its hydrogen into helium every second and radiates the difference outward as the sunlight falling on your skin right now. It tells us how neutron stars, collapsed cores of dead giants only about 20 kilometers across, yet more massive than our sun, pack matter so densely that a teaspoon of their material would weigh billions of tons on Earth. It tells us how black holes warp the very fabric of space and time so severely that not even light, the fastest thing in the universe, can climb back out once it crosses the event horizon. Our needle thought experiment isn't some isolated curiosity. It's a small, almost playful doorway into the same physics that governs the most extreme objects and events in existence. When you trace the logic of E equals mc squared all the way to its edge, you eventually find yourself standing at the foot of some of the most awe-inspiring phenomena the universe has to offer. And that, ultimately, is the real value of a question like, what if a needle hit Earth at the speed of light? It isn't really about needles at all. It's a lens, a deliberately extreme and impossible scenario designed to sharpen our intuition about a universe that behaves nothing like our everyday experience once you push its variables to their absolute limits. It reveals that the wall preventing anything with mass from reaching light speed isn't some cosmic technicality or bureaucratic rule. It's a fundamental, structural feature of reality, as real and as unbending as the fact that you cannot count higher than infinity. It reveals that mass and energy are two faces of the same underlying currency, and that speed, pushed far enough, can make even the smallest object rival humanity's most terrifying weapons. And it reveals, perhaps most beautifully of all, that our universe already runs this experiment constantly, quietly, invisibly, every single day, as cosmic rays flung from the most violent corners of the galaxy slam into our atmosphere and get gently, harmlessly absorbed by the very air we breathe without a second thought. So the next time you happen to notice a needle resting on a table, so light it barely bends light around it, so small it disappears into the texture of fabric, take a moment to consider the strange truth hiding inside it. Locked within that sliver of steel, according to the deepest law modern physics has ever written down, sits an amount of energy that dwarfs anything humanity has ever detonated. Energy that would need only enough speed and nothing else to come roaring out into the world. It never will, of course. The universe has made certain of that, wrapping the speed of light in a wall no mass can ever climb. But the fact that such destructive potential can sit so peacefully, so invisibly, inside something as unassuming as a needle, waiting on a rule of physics it will never actually break, might be one of the quietest and most humbling reminders of just how strange, how layered, and how astonishing the universe we inhabit truly is.